Welcome and hello. This is a video exercise in HEC HMS. And in this exercise, we are going to be working with the green amp loss method as well as the deficit and constant loss method. We'll be using these two different loss methods and changing the parameter values such that we want to match an outflow hydrograph that's observed using our computed results from HMS. All right, what you see on the screen here is the first link in the description. This is the green ant method we'll start with first. So what we want to do is just scroll down a little bit and then click on this zip file here and then click the download button. That will download, and then once we get the files up and loaded into our HMS project, we can start the steps. All right, so that's downloaded there. I'm going to go ahead and close that. And then we'll scroll down on this page and come back to it to start the steps in just a little bit. This zip file over here downloaded for me. I'm going to go ahead and open that up and then just click on the folders. Puxatawny is the name of the project. I'm going to copy that over into the location I want it on my computer. So I can close the original file and then, delete the zip file. All right, so I'm going to go ahead and open up this HMS file, puxatawny.hms in HMS. So I'll go File, Open, and then click on Browse and navigate to that exercise. All right, here's the directory, and then here's the .hms file, and select. Okay, the first thing I like to do when I'm starting these exercises and downloading a project that's partially built already is I'll click on the basin model and then just click on the basin itself. Here is our sub-basin. This is our entire watershed. It's got one sub-basin. It looks like it uses a grid for the precipitation. So if I click on meteorologic model, we have gridded precipitation here, as well as a monthly evapotranspiration. In the control specifications, if I click on that, it's called September 28th, and it starts on the 7th, and it goes through the 23rd. So we have about 2.5 weeks of simulation time that we'll be running at a 15-minute time interval. Now let's click on the sub-basin itself, this meteorologic element, and then scroll down to the components editor. What we see here is our discretization, canopy, transform method, base flow, and then loss method. So in this exercise, we're going to be dealing with the deficit and constant loss method, as well as the green and ant. Let's go ahead and start with the green and ant first. So I'll select that. And now I have a loss tab up here that I'll select in my components editor. The green and ant method has no means for extracting infiltrated water and therefore should only be used for event simulations. In this method, the soil is assumed to be uniformly saturated and infinitely deep. If you're following along the instructions, we can now scroll down on that page. And what it first does is it describes a number of the initial parameters and how to estimate them. So I'm just going to scroll past all this. And then about halfway down, we see this title, Modify the Existing HMS Project. And this is where we're going to start. Actually, we've already done the first few steps here. Open the project, click the sub-basin, you select green amp, and then click on the loss tab. So starting here in step 5, this is where we're going to enter our initial parameter values, which is shown in the screenshot right here. So let's go ahead and enter those values. For the method, we're going to select initial content, which it's already selected there for me. And then for the initial content value, I'm going to say 0.1, saturated content 0.41, suction is 5.6 inches, and then the hydraulic conductivity is 0.2 inches per hour. The percent impervious, I'm going to leave at 0% for every trial of both the green ant and the deficit constant. So you can just keep that at 0%. Next, it tells us step 6, create a new simulation run and then run it and then view the results. So that's basically steps 6 through 9. Okay, so I'm going to go up to the components menu, click simulation run manager, click new to create a new simulation run. The instructions tell me to call it September 28 underscore green amp. Next, here's the basin model, here's the meteorologic model, and then here's the control specification, and finish. All right, so there is my simulation run. The only thing now to do is select it up here in the compute toolbar and then click the compute button. So that was a quick compute. It's done. Let's take a look at the graph and the summary table. So with the sub-basin still selected, we'll click on the graph icon here. And what we see on the top is the hydrograph, and then on the bottom is the hydrograph. As you can tell, there's way too much loss. This black line of the hydrograph is the observed flow at the sink or the downstream end of our subbasin. And then the blue line here, which is the outflow hydrograph computed by our model, shows that there's basically all the precipitation is lost and none of it runs off, except for a little bit in this second and smaller storm on the 18th. So this plot just basically tells me there's way too much loss. We need to dial down some of our parameters so that there's less loss, less infiltration. I also want to point out that the summary table right here keeps track of our peak discharge values and the total of runoff in terms of inches, as well as a few statistical metrics that help us compare how close the model output is to the actual observed data. We'll be returning to this table to look at the results in the other trials as well. The next task in this exercise is to change these calibration values. So what it says in step 1 is to change the hydraulic conductivity from 0.2 to 0.05. That's this right here. Okay, so I'll go ahead and click save and then rerun that same simulation. So I'll do that right now. Okay, so that's done. I'll click the graph button, and now we can see that we actually have some runoff, which is good. It's not perfect, but much better than it was. Up in the top plot, we see the Hyedo graph, and this shows us the total precipitation is in blue. And then on top of that, if I click in red, this is the loss. So the blue you're seeing in this image here is the total precipitation that was not infiltrated or not lost, hence contributing to the overland flow. In the bottom plot here, we see, again, the same black observed flow hydrograph, but now the blue hydrograph has a much better match, at least for the first part of this rising limb. We're definitely short on the peak discharge on this first storm, but you can see that we overestimate on the peak discharge on the second storm a week later. So I'll close that. And if we look at the summary table, we can now do a reasonable comparison between the peak discharge, which is about 5,000 CFS, that's computed, and then our target is about 7,800. The total volume we're aiming for is 4.4 inches, and then our results here gave us 3.46 inches. Next, the instructions tell us to change the section in inches from 5.6 to 7.5. So if that's changed to 7.5 and we hit save, then let's go ahead and run the simulation again. That's done. Let's go ahead and check the plot. And what we see is similar results as before. We increased the suction, which basically means there's going to be a little bit more loss. In fact, I'm not quite sure why we made this change because we were already under on our peak. And it looks like we're still over on the peak of the second plot of the second storm. And then right here is the summary table. We're below on peak discharge and then also quite a bit below for total volume. On step 2, part C, this is going to be our fourth trial. This is the last change I'll make for green amp. It tells us to change the hydraulic conductivity from 0.05 down to 0.025. There's that change. And then I'll click save. And then let's run this simulation. Okay, that's done. We should see less losses and a better match. Here's the results from that. What we see is less losses. Certainly in this first storm, we have an overestimation of the volume of from our computed results, but we still don't quite hit that peak discharge. The second storm is also off quite a bit. We're definitely overestimating the computed hydrograph versus the observed hydrograph right here, both in volume and peak discharge. After that, the instructions tell us to continue adjusting the parameters for this grain amp method to hopefully match the peak discharge and total volume compared to that observed hydrograph. Next, I want to bring up the results that we've attained through the green amp method. This right here is our first trial. This observed value and observed value here won't change for all the trials. What we have is a computed peak flow and a computed total volume based on these initial values, the parameter values that we were using. So we have a percent error and for both of these metrics as well as the Nash-Sutcliffe value. This first trial was, as good as guessing. This second trial was definitely better than the first, but we're still off by quite a bit. The Nash-Sutcliffe value increased to 0.78. Again, we're looking for a value of 1, ideally, and that came as a result of decreasing the hydraulic conductivity from 0.2 to 0.05. In the third trial, we increased the section to 7.5. In fact, the results actually worsened slightly. And then our fourth trial was about as good as the second trial when we decreased the hydraulic conductivity again. What we see from this plot is that using the green ant method of loss is similar to the initial and constant method, where if we don't have evapotranspiration, then our second storm is not going to have any way to remove the precipitation except through the saturated hydraulic conductivity. And that's just not realistic. Methods like this should only be used for single event storm simulations. However, we're in luck. So in the second half of this exercise, starting now, we're going to be looking at the deficit and constant loss method in HMS. This method allows for continuous simulation when used in combination with a canopy method that will extract water from the soil in response to evapotranspiration computed from the meteorologic model. So what that means is I'm going to go back to the subbasin tab here. We're going to change this loss method to deficit and constant and then save. When you make that change, you may get a message that says, hey, you're going to lose your parameter data for the previous method. Just say okay to that. And what that means is if I click on loss, now I just have a new set of parameters for that deficit and constant loss method that we just selected. I also mentioned evapotranspiration, and we looked at this at the beginning of the video. What we have in our meteorologic model up here, MRMS, is evapotranspiration. And what we're seeing is a monthly average. So for the month of September, we're going to have 3.5 inches per month of evapotranspiration. So working with the canopy method, this will actually serve to increase the losses and therefore the outflow hydrograph from our computed second storm on the September 17th and 18th will have more losses and hopefully match that observed hydrograph more closely. If you're following along in the online instructions, go ahead and click that second link. Or if you want to, you can just navigate there from this page here by going down to the loss methods. This is green amp, and then the next one down is deficit and constant. All right, so what we have on this page here is our instructions again. The first thing you can do is download these initial files. You don't have to do that if you already did that for the green amp earlier in this exercise, but they give you that option here if you are starting with this deficit and constant as your first exercise. All right, as before, they talk about the method in general and then talk about the different parameters and how to determine good initial values. We're going to scroll down to the actual instructions, which start right here. Modify the existing HMS project. We're going to start with step 4 here, where we select the loss tab and then enter the data. These are going to be our initial values here, 27, 0.2, and 0. So back to the subbasin, and then I'll click on the loss tab here. What did I say? 2, 7, 0.2, and 0. Again, percent impervious will always be 0 for this exercise. Our initial deficit is estimated to be 2 inches, maximum deficit 7, and then the constant rate of infiltration is 0.2. So I'm going to go ahead and save that, and then I'm going to create a new simulation run. So what we did before was create a simulation run for the green ant method. Now we're going to create a simulation for the deficit and constant. So compute simulation run manager, new. Go ahead and give this a name. Okay, next, next, next. And then here is our simulation. We're ready to roll. I'll go ahead and select that new simulation. Save. Everything else in the project has been already created and set up for us, like the meteorologic model, the control specification. All we have to do now is click the run button. So that's ran. Let's take a look at the plot of the subbasin. So there is the plot. As before with our first trial with green amp, our first trial now with deficit and constant shows way too much losses. So I kind of find it funny they take so much time and effort getting those initial values and then having such a garbage results. So you can pretty much guess initial conditions and get results this good. Let's go ahead and continue on to the next step. Down to the next task, if you scroll down on the instructions to calibrate the model, the step numbers reset. So step 1 under that heading, part A tells us to change the deficit and constant parameters from initial deficit of 2 inches down to 1 inch, and then from the constant rate of 0.2 inches per hour down to 0.1 inch per hour. All right, so let's go ahead and hit save. And now we're going to run this trial. This will be our second trial. Okay, so that completed. Now let's take a look at the results. And thankfully, our results look a lot better than they did for the first trial. What we see here in the hydrograph is the rising limb matches the observed flow like almost perfectly, at least for up to about 3 or 4,000 CFS. So in blue here is the computed results. black is the observed results. Clearly, we missed on the peak discharge, but at least we got more volume. If I scroll over to the second storm, what we see is somewhat promising, even though it's off by quite a bit. It appears that we're also off by about 50% of that peak. Therefore, I think it's possible to get more accurate results using deficit and constant than green amp or initial and constant loss methods due to the ability of water to be removed from our system via the canopy method and evapotranspiration. Next, what I'm going to do is look at the summary table. So here is that. We've seen this already before. The observed data is all the same, but what we have is a peak discharge of 3964 and then a total discharge volume of 2.40 inches. All right, now we're on to step 2. And in part A, it tells us to change the constant rate of infiltration from 0.1 to 0.05. So here's 0.1, and then there's 0.05. I'm going to click Save and then compute. This makes sense because we had too much loss. So if we reduce the constant rate of saturated infiltration, then we should have less loss. Let's look at the plot. So what we have on the plot is an overestimation right here in blue initially for the first storm, and we're still a little bit below the peak discharge, but yeah, too much volume here. The second storm is a lot more promising. It looks like almost a perfect match, at least on the rising limb and the peak flow. But then on the receding limb, it looks like we could probably use a little bit more base flow. Up here in the top plot is the Haito graph. So if I click the zoom tool and then take a closer look at that, that initial abstraction takes place through about late morning of September 9th. And then the infiltration rate decreases to its saturated level, which is 0.05 inches per hour. Now, what we're seeing here is not 0.05 inches per hour, but this is a 15-minute time interval. So we're really looking at the number of inches per 15 minutes. We have to divide that hour by 4. 0.05 divided by 4 would be 0.0125, which is what this line is at right here. This horizontal line separating the red and the blue colors here. Red representing the losses, and then blue representing the volume, or excuse me, the depth of precipitation that contributes to the overland runoff. If I zoom out, we need to address this excess volume right here in the rising limb of the first storm. So to do that, we're going to increase the initial deficit in our parameter values and then return to the plot and see what this looks like. Before we do, let's, as always, take a look at the summary table and then capture those results. Our Nash Sutcliffe value is up to 0.785, and I think it's going to actually improve a little bit more with this final change. All right, like I said, we're going to increase that initial deficit from 1 to 1.75. This is step 2, part C, if you're following along, and save. All right, one final simulation run, and then we'll check out the results. All right, here's the table. And as we see, we have less volume in that rising limb of the first storm. I would say the total volume of this first storm and the second storm are probably the best we've had yet. However, we're having trouble matching this first little bump and then the peak discharge that's demonstrated here with the black observed hydrograph data. In blue here is the computed hydrograph. In part 3, we conclude that it's difficult to match the peak discharge and the peak volume. It's also this first storm here has this double peak on the observed flow, first this first one and then the second one about a day later. And it's nearly impossible to recreate this double peak type of hydrograph using only a single subbasin. To better model this response, 2 or more subbasins should be delineated and used in the model. All right, let's go ahead and look at the summary table for this last trial we did here. 6,782 is still about 1,000 CFS shy from our target peak discharge. And then our total volume here of 3.84 is still quite a bit less than the volume. However, the overall shape of the hydrograph on this final and fourth trial that we ran was definitely the best, resulting in a 0.904 Nash-Sutcliffe score. I do realize that there is an RMSE standard deviation and percent bias values as well, but I just kind of prefer working with Nash-Sutcliffe. And here are our results. This is what we were looking at for green amp, but I'm going to combine the data together. So our first trial using deficit and constant is shown here. Not the best results, so let's just go to the second trial where we decreased both the initial deficit and the constant rate of saturated infiltration. So we have a positive Nash-Sutcliffe value. That's good. In our third trial for deficit and constant, we had probably our best values compared regarding the matching the total volume and peak discharge with being just 10% off and 1% off our values. And our Nash-Sutcliffe score increased as well. And then the final trial, we had the best Nash-Sutcliffe score, which was the result of increasing that initial deficit value. Well, that's it for this exercise. We looked at the green amp loss method as well as the deficit and constant loss method, changed the parameters, ran some simulations, looked at the results, and drew some conclusions.